Let's go over this example where we're asked to analyze the critical points of f of x equals 1 minus x to the 2/3. So let's start by, this is an example. The function is something that has come up before, and that's what I wanted to use as an example. So analyze the critical points of function like this it's kind of unusual for in terms of the applications that we've seen so far, because the derivative of f this is something we computed before, but it's just a chain rule. This is a power function. It's 2/3 minus 1, which is minus 1/3. And so in fact, f prime is not defined at x equals 1. So what does the function look like? So we have 1, and we're coming from one side and making a cusp as you approach 1. So if you look at the slopes of the tangent lines, you see here that the slope is becoming more and more negative till it reaches minus infinity. On the other side becomes more positive, so it's approaching plus infinity. But at any rate, the derivative at this point is not defined. There's no, you only have, if the only candidate for a tangent line will be a vertical line, so that's not, the slope of the tangent line will not be defined, so it's not, in fact, doesn't have a tangent line. That's not a function of x. So this is 1 minus x to the 2/3. Now that we've seen what happens when we approach 1, we can safely say that f prime at 1 is not defined. And since it's not defined, f prime not being defined at x equals 1 implies 1 is a critical point, right? Remember that critical points are points which the derivative is not equal, it's equal to 0 or is not defined. Since it is not defined, then it is a critical point. So the idea here is to go over a less common example where the critical point you're asked to analyze is not a point at which the derivative is equal to 0, but rather a point where f prime is not defined. Nevertheless, and we can see, we're just going to confirm what we see here in the graph of the function. Let's notice that for x less than 1, f prime, which is equal to minus 2/3 times 1 over 1 minus x to the 1/3 is negative. Remember, if x is less than 1, that means that this quantity here is positive, and if you raise it to the 1/3, it's going to be positive, and you're multiplying that by something negative, so it's going to be negative. For x greater than 1, f prime still the same, so the same formula. But now what you have inside of the parenthesis is now negative because x is greater than 1. So 1 minus x is negative. Minus times minus 2/3 is going to be positive. And so this tells us that at x equals 1, the derivative changes from, the sign of the derivative changes from minus to plus. So f prime changes from minus to plus at x equals 1. So that means, that implies that 1 corresponds to a local min. Right, and we can confirm that by simply looking at the graph here. So 1 is a point at which 1 minus x to 2/3 doesn't continue decreasing any further after you reach 1 from the left, and it starts increasing after, so it's a local min. There are no smaller values than that for this function, 1 minus x to the 2/3. And you can never take on a smaller value than 0 because the original function is 1 minus x to the 2/3, and this is the same as 1 minus x to the 1/3 squared. And a squared is always greater than or equal to 0 for a real number. So that means that our analysis is consistent with what we would expect. So the function attains a local min. In fact, it's a global min. Number in which it attains 0, which is the smallest possible number that a square can achieve. And the analysis using the first derivative test tells us the same thing. F prime, the sign of f prime changes from minus to plus, which implies that 1 corresponds to a local min. The important and the unusual thing about this example is that this critical point, this is the only critical point of the function f, it's not a point at which the derivative vanishes, but rather a point where the f prime is not defined. So that's the only point I was trying to make with this example.